All right, welcome to another deep dive with us. This time, we're looking into Skolem's paradox. And, I think this is particularly juicy for you since you're coming at this from, well, a philosophical background. We're really talking about the nature of knowledge itself here and how we grapple with the infinite.
Yeah, absolutely. I mean, what we have here is a real head scratcher, right? We have these two fundamental ideas in logic that seem to be totally at odds with each other.
Okay, so let's lay those out. First, we've got Cantor's theorem. It basically showed us that there are different kinds of infinity.
Yeah, exactly. Not all infinities are created equal. You have things like the natural numbers 1, 2, 3 going on forever, and those are what we call countably infinite.
Right, you could imagine listing them out, at least in principle.
You got it. But then Cantor came along and proved that some infinite sets are even bigger.
Like the real numbers.
Exactly. All those decimals going on and on, those are uncountably infinite because you can't match them up one-to-one with the natural numbers.
So he developed this idea of cardinality to compare the sizes of infinite sets.
Right. Two sets have the same cardinality if you can pair up all their elements perfectly. A bijection, we call it. Cantor showed us that there's a whole hierarchy of infinities out there.
Okay, so we have this whole concept of uncountable sets established, and then enters the Lowenheim-Skolem theorem.
And this is where things get really interesting. It essentially says that if a theory, like set theory, how we talk about collections of things, has a model at all, it'll have a model that's countable.
Meaning all the stuff in the model can be listed out.
You got it. It's like saying, even if you have a theory that describes a universe with huge, uncountable sets, you can still find a way to squeeze all that into a framework where everything can be counted.
So hold on, how does that even work if our theory, like ZOC, that's the Zermelo-Fraenkel set theory, with the axiom of choice, explicitly talks about uncountable sets?
Well, that's the heart of Skolem's paradox, right?
Yeah.
If ZFC has a model, the Lowenheim-Skolem theorem guarantees it'll also have a countable model. Let's call it M. Now, inside M, there's got to be some element, let's call it M hat, that satisfies the formula for being uncountable.
Meaning, from M's perspective, there's no way to pair up the elements of M hat with the natural numbers.
Right. But here's the rub. M itself is countable. So everything it contains, including what it thinks are the elements of M hat, should also be countable from our outside perspective.
So it's like M is saying, hey, this set M hat is uncountable.
Yeah.
But we're looking at M itself and thinking, but you're countable, dude, so how can that even be possible?
Yeah, that's the paradox. From M's point of view, it's doing everything right. It's following all the rules of set theory, and it's come to the conclusion that M hat is uncountable. But we, looking in from the outside, see a different picture.
Now, isn't this just a matter of, like, any model being a simplification? Like, a map of a city can't possibly include every single detail.
It's tempting to think so, but there are a couple of things that make Skolem's paradox trickier. First, these first-order models actually do a pretty good job of capturing a lot of set theoretic concepts accurately, like, the idea of an empty set or having two members, even the concept of infinity in some cases. It's just when we hit this countable versus uncountable distinction that things seem to get weird.
So it's not that the model is just inherently limited in its scope. It's succeeding in a lot of ways, and then failing in this very specific way.
Yeah, and here's the other thing. This paradox isn't tied to some weird specific choice of axioms. No matter how you try to set up a first-order axiomatization of set theory, you run into this issue. It seems to be baked into the very logic we're using.
Okay, so that's why this was so philosophically troubling, even though, mathematically speaking, it doesn't actually break set theory.
Right. Skolem himself wasn't trying to say that set theory is inconsistent or anything. It's more that it reveals something very strange about our formal systems and how they relate to the mathematical reality they're supposed to describe.
Right, because from what I'm gathering, the paradox itself isn't a mathematical contradiction, but more of a philosophical head-scratcher.
Exactly. As Van Huygenoot put it, it's a novel and unexpected feature of formal systems, not a logical breakdown.
So help me unpack this a bit. Where does the paradox actually come from?
Well, we have to be really careful about how we interpret the language of set theory, especially that formula for uncountability. There's how we'd normally understand it, and then there's how it's understood inside that countable model, M.
Okay, so if I'm understanding this right, when we use a formula like X is uncountable, in our everyday math talk, we're thinking about the real membership relation, like what sets actually contain what other sets and are for all, and there exists, are ranging over all the sets we can imagine, right?
Exactly. That's what makes Cantor's proof work. He showed that if you try to pair up all the real numbers with the natural numbers, you'll always miss some.
Right. But inside M, things are different. The membership relation is just whatever M says it is.
It's just a relation on those specific things that exist inside M, not necessarily real set membership. And the quantifiers for all, and there exists, those are only talking about stuff inside M, not this whole vast universe of sets we think about.
So M could be saying these two things are members of each other, even though, from our perspective, they might not even be sets at all.
Yeah, that's possible. And when M says something like, there's no function that pairs up M hat with the natural numbers, it really means there's no such function inside me, in my little world. But we looking in might see that, yeah, in the bigger picture, there totally is a function that does that.
So the paradox is a result of this kind of mismatch between the way we interpret the language of set theory and the way M interprets it.
Yeah, it's like we're speaking different dialects of the same language.
And the sources we've been looking at, they also talk about these things called transitive models.
Right. Those are special because in a transitive model, the membership relation inside the model actually lines up perfectly with the real membership relation, at least for the sets that are actually inside the model.
Oh, interesting. So in that case, how does the paradox work?
Well, in a transitive model, it all comes down to the quantifiers. The model can only see the things that exist inside of it. So if it says there's no bijection between omega and m hat, it's technically correct because it's only considering the functions that exist as objects within the model.
But we know such projections might exist out in the bigger world of all sets.
Right, but the model, with its limited scope, can't see those.
So even when the model gets membership right, it can still be wrong about cardinality because it just doesn't have a big enough perspective.
Exactly. It's a fascinating limitation of first-order logic. If we were using a more powerful logic, like second-order logic, this wouldn't happen.
Now, there's still something bugging me. How does a countable model even manage to satisfy all the axioms of ZFC? Like the power set axiom, for example. That seems to very clearly imply uncountable sets.
Countable models are sneaky. They find ways to satisfy the axioms, but in a way that's, well, limited by their countability.
What do you mean?
So take the power set axiom. It says that for any set, there's another set that contains all its subsets. In a countable model, the power set of a set only contains those subsets that are also in the model.
So it's like the model is pretending that a whole bunch of subsets don't even exist.
In a way, yeah. It's like it's saying, okay, I know the power set axiom says this should exist, but I can only work with what I have. It's a limited interpretation of the axiom, but it still technically satisfies it.
I see. The sources mention Resnick's example. This set of real numbers inside one of these countable models would be pretty disappointing.
Right. It wouldn't contain most of the real numbers we think about. It would only have those that happen to be inside the model.
So even though it's called a set of real numbers, it's not really the whole thing.
Nope. And this kind of misinterpretation, we could call it, happens across all the axioms. It's how the model manages to stay consistent while still being countable.
Okay, so it's really the limitations of first-order logic that are at play here.
Right. And that brings us to the philosophical heart of the issue. What does this tell us about how our formal systems connect with mathematical reality?
Right. I mean, even if we take a formalist or model-theoretic view where math objects are just whatever satisfies the axioms, there's still this weird tension.
Yeah, there's the quantification inside a specific model, and then there's this idea of quantifying over all possible models, and those two things can be very different.
Now let's talk about Skolem himself. The sources say he drew some pretty significant philosophical conclusions from this paradox.
Yeah, he was concerned about using set theory as a foundation for mathematics. He saw this paradox as evidence that set-theoretic concepts, like uncountability, are inherently relative.
So not like absolute truths.
Right. He was leaning towards an algebraic or model-theoretic view of axiomatization. In this view, the axioms of a theory don't describe some single special model. They just define what it means to be a model.
So there could be many different models that fit the bill.
Exactly. And each model would have its own way of understanding concepts like set and membership. There wouldn't be one correct interpretation.
And that's where the relativity comes in.
Yeah. Skolem argued that the Lowenheim-Skolem theorems show us this relativity in action. We can have a countable model that thinks a certain set is uncountable, even though we know it's not absolutely uncountable.
Okay, and this isn't just some trivial kind of relativity, right?
Right. It's not like we're saying the empty set could be different in different models. It's about concepts that are tied to infinity, like uncountability, which first-order logic can't seem to pin down.
So the sources actually present a few different ways to interpret Skolem's overall philosophical argument.
Yeah. There's the traditional view, which sees him as attacking set theory head-on, arguing that the paradoxes in set theory force us to adopt this algebraic view, and then the relativity just follows from that.
And then there's the foundationalist view.
Right, right. That view says that Skolem was more concerned with finding a secure foundation for mathematics, and he saw set theory as shaky. The paradox in this view is just one piece of evidence against set theory's foundational claims.
And then there's Gené's interpretation.
Yeah, which is more focused on the concept of uncountability itself. Gené argues that Skolem was essentially saying that there's no good way to introduce uncountable sets into math in a rigorous way. The paradox shows that even our axioms don't force us to accept uncountable sets, and any attempt to get around the paradox seems to already assume you know what uncountability is.
Oh, I see. It's like a circular argument.
Right. Now, of course, there have been responses to Skolem's paradox over the years. Zermelo suggested using second-order logic, and Tarski proposed type theory as a foundation.
But Skolem probably wouldn't have liked those much, right?
Probably not. He was pretty committed to first-order logic.
So this brings us to the idea of Skolemite skepticism.
Yeah, this is the view that takes Skolem's paradox very seriously. It says that maybe those theorems are right, and the notion of uncountability really is relative.
And some even go as far as saying that all sets are absolutely countable.
Yeah. The reasoning goes something like this. The algebraic conception of axiomatization is the right one, and this is often motivated by a rejection of Platonism, the idea that mathematical objects exist independently of us.
So if we accept that, then the paradox shows that set theoretic notions are relative. And then we can push that further and say, hey, if every set has a countable version, then maybe they're all just countable.
But there are a few problems with this line of thought. First, you need a reason to accept the algebraic view in the first place, and you can't just base that on the paradox itself, otherwise you're arguing in a circle.
Right. And there are other criticisms of Skolemite views. Some people argue that there's no problem with realism about sets, that the paradox doesn't actually force us to give up that view.
And there are problems with the algebraic view itself. It's not clear how it can account for all of mathematical language, and it might lead to changes in how we actually do math that many people wouldn't like.
And there's the whole issue of why we should privilege the countable models. If the upward Lowenheim-Skolem theorem says there are uncountable models too, then why are the countable ones the true ones?
Exactly. So Skolemite skepticism definitely has its challenges.
So we have all this debate around countable and uncountable models, and then there's Joel Hamkins and his multiverse view of set theory.
Right. He says that instead of trying to find one true model of set theory, we should accept that there are many, and they're all valid. Set theory, according to this view, becomes about exploring all these different models and how they relate to each other.
That's a pretty radical departure from the idea of finding one true model.
It is, but it's motivated by how set theorists actually work. They're constantly building and comparing different models.
And in a way, this aligns with the algebraic conception, right?
Definitely. And it kind of gives a new spin to that Skolemite intuition about everything being countable. In the multiverse, every set can be countable in some model. But that doesn't mean it's absolutely countable. It just means cardinality is kind of fluid. It depends on which world you're in.
So this whole idea of countability gets really complex in Hamkin's view.
Yeah, it's not just a simple yes or no.
Now, finally, we have to talk about Hilary Putnam and his model theoretic argument against realism. He basically took Skolem's ideas and used them to argue that language, including the language of set theory, is fundamentally indeterminate.
Right. He's saying that even with all the rules and constraints we put on meaning, there might still be multiple ways to interpret our words, even in something as precise as set theory.
And he draws on Skolem's paradox for this, right?
Yeah, big time. He uses a theorem that depends on the Lowenheim-Skolem theorems to show that even for a well-defined theory like ZF, with the axiom of constructibility, VL, there are models that contain any countable set of real numbers you want. So even a statement like VL, which seems like it should have a definite truth value, could be true in some weird model we didn't intend.
So even though we try to pin down what our words mean, there's always a chance we're missing something.
That's the worry. But of course, Putnam's argument has its critics too. Some say there are technical issues with applying the Lowenheim-Skolem theorems to proper classes, and others point out that he seems to rely on finitude concepts while questioning the determinacy of infinite ones.
Right, and there's that whole debate about what makes a model the intended one.
And then there's the question of whether Putnam is just adding more theory to try to fix the problem rather than actually addressing the underlying issue.
So, as with everything in philosophy, there's no easy answer here.
Nope, but that's what makes it so interesting.
All right, so let's wrap things up. This deep dive into Skolem's paradox has shown us that what seems like a simple logical puzzle can actually open up a whole universe of questions about the nature of math and how we know things.
Yeah, it's not just a matter of getting the math right. It's about what the math means, about how our formal systems relate to reality, and even about the limits of logic itself.
And even though it's been almost a century since Skolem first presented his paradox, it's clear that the questions it raises are still very much alive today.
Absolutely. And for someone like you coming at this with a philosophical mindset, I think Skolem's paradox offers a really rich vein of thought. It forces us to re-examine our assumptions about what math is, how we do it, and what it tells us about the world.
And our dive today is just the beginning. There's so much more to explore in model theory, philosophy of mathematics, and the debates around realism and anti-realism.
Yeah, the relativity that Skolem uncovered is still sparking some of the most interesting discussions in those fields, making us constantly rethink what we think we know about mathematical truth.
So keep exploring, keep questioning, and keep diving deep.